or other instruments such as Hubble or JWST, etc. And the other is the cold gas component. It generally has a temperature range of few tens to hundreds of Kelvin, and that can be detected with radio, 21 centimeter line using ASCAP telescopes or any other radio instrument. And the third is the hot gas component, which is generally unbound to galaxies, and these can be detected with X-rays or techniques like Zunyaev-Zeldovich effect, and these generally have a temperature range of something about 10 to the 6 Kelvin or more. And where do I want to look at these systems? I want to look at them in things called galaxy groups. So what are galaxy groups? These are systems with two or more galaxies that are held together in a common gravitational potential. And here are just a few examples of such galaxy groups. And the most important component, the most important property of a galaxy group would be its mass, the total mass, which is commonly known as a halo mass, which includes the mass of the dark matter as well as the baryonic matter. And generally, the groups have mass ranging from 10 to the 11 solar masses to roughly 10 to the 15 or slightly above. And usually, very high mass groups above 10 to the 14 solar mass are generally referred to as clusters. But in this talk, I'll be referring anything with two or more galaxies as groups in my work. So you might even know most of these groups. The one on the top left is the Stephan's quintet, and on the right is the Joe Biden's cluster, or the SMACS cluster as it's known as. So these groups, we can measure the number of these groups within a particular volume as a function of halo mass, and these are known as halo mass function. This is basically a histogram that shows us at a particular halo mass bin how much groups are present. And if we multiply the number density, which is on the y-axis, with the x-axis on the halo mass, we get a plot of mass density as a function of halo mass. This is important because if you integrate under this curve, you can get the total matter density. And here you can clearly see that the most of the matter in the universe is present somewhere around 10 to the 12 solar mass or more. And more focused, we can see that the majority is around 40% is present between 10 to the 12 to 10 to the 14 solar mass. And hence, this is why we need to study groups. It's not just sufficient to study individual galaxies, which may be on the lower side, or large clusters, which have been studied with X-rays, which would be about 10 to the 15 or 14 or more. The group regime is very particularly important. And now, moving forward. So now that I've introduced what the baryons are and where I'm trying to look at it, I'll introduce the method that I'm trying to use it using very scientifically accurate plots. Shown here is the halo mass function, which I'll be multiplying with some kind of scaling relations, which could be a stellar to halo mass relation or H1 to halo mass relation. And the resulting thing would be a baryonic mass density as a function of halo mass. And this again, if I integrate under the curve, I would get a mass density. And if I divide it by the critical density, I can get the omega baryon value for a particular component. And this I can add up for different components and match with the cosmological constraints from Planck measurements of the 5% that we are getting. Now going into some real data. So shown here is a stellar mass to halo mass relation spanning from 10 to the 10 to 10 to the 15 solar mass, with most of the data about 10 to the 12 coming from gamma. And I've added a few more data sets to go down to lower halo masses. And if I multiply this with the halo mass function that I showed previously, I would get a plot something like this, rho star as a function of halo mass. And integrating under this, I can obtain the omega star value. And I've shown below the value of omega star that I get if I integrate all the way down to 10 to the 6. And that's a value of roughly 2.1 times 10 to the power minus 3. But this is just a technique and this is just a value. So I need some way to cross-check this. So this is not the only way to measure omega star. Omega star has been measured several times using way better methods, which have much lower errors. And that's mainly using galaxy stellar mass functions. So with the latest measurements from gamma DR4 work, we have a value of 2.2 times 10 to the power minus 3. And we can see that this is quite consistent with the value that I said previously. So this is like a proof of concept to my method that I can use this for measuring baryon densities for various components. Now I can apply this to H1. Again, here is a H1 to halo mass relation with most of the data sets about 10 to the 12 showing groups, data for groups. And below 10 to the 12, because we don't have particular detections, I've used the Sparks dataset, which are isolated galaxies for which we have very good rotation curves, and hence we can measure the halo mass. And again, this we can multiply with the halo mass function and get a plot of rho h1 as a function of halo mass. and I get a omega H1 value of 0.4 times 10 to the power minus 3. And similar to stellar, even for H1, there have been studies conducted using other methods where we can get very good omega H1 measurements. And here is in the inset plot, you can see that at redshift 0, the measurements are around 4, 10, 4, minus 4, which is again quite consistent with what I said. Now that this method seems quite robust, we can apply it to X-ray or hot gas component. That is where we don't have other measurements to get the omega X-ray values. So here is a plot of hot gas mass or plasma mass or X-ray mass, whatever you want to call, as a function of halo mass. This I have collected from several literature data sets. But the important thing to see is the halo mass range that this data set covers. It's just roughly around 10 to the 13.5 solar mass or more. So we don't have measurements for lower halo masses. That is where this method and future works are quite important, because for H1 and stellar, we had measurements nearly all the way down to at least 10 to the 11 or 10 to the 10. Now, even for this, if I multiply the halo mass function with the scaling relation, I can estimate omega X-ray value, for which there is no cross-check to do. But because for the H1 and stellar, it was a proof of concept correct method, we believe this also could be potentially correct. So all good till now, 3 scaling relations, wonderful. But more interesting things come when we combine all the 3 data sets. So I'll show them as a function of, as a baryon fractions. So by baryon fraction, I refer to the total baryonic mass divided by the halo mass. So that I'm plotting as a function of halo mass. And the magenta line shown here is the cosmic baryon fraction from Planck measurements, which is a value of around 0.15. And the dotted line shows 75, 50, and 25% of that. So putting the H1 data on this, it shows that H1 is quite subdominant, the highest halo mass end, and it peaks around 10 to the 11. And we can add stellar on top of this. They peak around the 10 to the 12 solar mass regime, which is quite known from the stellar to halo mass relations. And the X-rays come at the high halo mass end. So this is like a wonderful work that I believe, because at the highest halo mass end, if we see around 10 to the 15 solar mass, you can see that it's like a very closed system. That is, we are matching with the cosmic baryon fraction. However, when you come down anything below 10 to the 14 solar mass, we are less than 50% of the cosmic baryon fraction. So we have some baryons which are missing, but this is not the first work which has shown this. So here in black line, it's the total, which is the sum of the red, green, and blue. So there have been studies, this is one from last year, in which they used X-ray clusters of around 100 clusters, in which they measured X-ray measurements, and they had corresponding stellar measurements from SDSS. Even here, you can see that anything below 10 to the 14.5, they are missing. They are not able to account for the baryons that are present. So where could these baryons be? So there could be 2 particular reasons. One is the 3 components that I'm looking at here are the plasma, stellar, and H1. But these does not include the so-called WIM, or the warm hot intergalactic medium. So the plasma goes about 10 to the 6 Kelvin, cold gas a few hundreds, a few thousands of Kelvin at max. But there is this temperature regime around 10 to the 4 to 10 to the 6 Kelvin in which gas could be present, which cannot be detected by X-rays, or it's basically very difficult to detect. So this missing could be in that form, or else the baryons may not be inside the halos itself. They could be ejected outside halos. And that have been shown recently by few simulation results. Shown on the left is from TNG, and on the right is Eagle. Just quickly going through the TNG, you can see the brown line is for 10 to the 15 halo mass, and the other colored lines for anything below 10 to the 15. And the dotted line shows the virial radius. So you can see that for all halos less than 10 to the 14, we have to go out to large virial radius to match the cosmic baryon fraction. So this points out to the fact that the baryons may be outside the halos. And on the right is a similar result by Eagle, which shows that nearly 60% of the baryons have been ejected. So those could be the 2 possible things that's happening. So in summary, the 3 baryon components that I have looked for in my work are the hot plasma, stars, and neutral gas. And I've looked for them in groups. And I have preliminary measurements for the total omega baryon. And hopefully, we can do some stacking experiments to at least get the X-ray data set to further lower masses with some quite robust measurements. And we need further techniques to measure maybe gas in the form of WIM or something else. That's all. Thank you.